Hey everybody, and welcome to the next TempleOS tutorial. In this one I'm going to be talking about max pooling. And max pooling is really important for convolutional neural networks because they reduce not only the spatial dimensions of our images, but they help us to extract the prominent features of the image through the max pooling algorithm. And the max pooling algorithm is really useful because it takes the most prominent color values from an image, and it also emphasizes the stable features, reduces noise, and makes transitions, other operations that we perform on images that are large, simpler. It also can help to make large images more in line with some of the smaller images in our data set. So it's really useful. It's not the only pooling algorithm that's out there, but it's a very useful one, and I'm going to go over it today. Hey everyone, so I'm going to do a quick demonstration of how max pooling works. Here we can see our input is a 5x5, let's assume it's a BMP. And this is a matrix, and we have a kernel which is defined by a size. In this case, it's 2 by 2. So we have a 2 by 2 kernel and we have a 5 by 5 input. In order to perform max pooling, we're going to take our kernel and run it over the first position in our input. So we're going to have a 2 by 2 box here. And this matrix that comprises our BMP has color values. So technically a BMP is actually a tensor where it has 3 of these. We can think of it like a cube. And we're going to run max pooling on each one of these dimensions. But for now we could just think of it as a single matrix. So this particular matrix, let's say it's for the red color values. The red color values, this might have 0 red. This might have 0 red. This might have 255 red. This might have 150 red, and it might have 25 red here. So we're going to take our kernel and put it here, and we're going to say which is the maximum value of these. And well, clearly it's 255. So we're going to take 255 and put it in our output. And we want to move the kernel now. So how we move the kernel is dependent on a variable we call the stride. So if the stride in this case is 2, we're going to move the stride, we're going to move the kernel by the stride, which is 2. So we're going to move it from the starting position, 1, 2, and it will be right here. And we're going to have the second kernel right there. So you can see here that if we could take the red values from here and run a pooling operation again and then add another sector to our output. If we keep doing this, and when we get to this end here, we can see that, well, our kernel isn't actually going to fit. There's only a 1 by 2 space here for us to read from. In this case, we want to apply an operation called padding. And padding, all that does is it adds extra cubes to our image so that our kernel can go and stride over the entire image and run its max pooling without going into a void or a null area. So when we add these paddings, and these paddings just have 0 in all of them, when our kernel finally gets to this part, it actually has some data to pool from. So let's say here it's 150 and here it's 25. And then we could just fill in random values for this second part here. So in this part it's 75 as the max value. And in this third part, because we've added our padding, we can see that 150. And we can just apply the kernel. So we're going to go to the next row here with the stride of 2. Stride of 2. And you can see that our kernel fits nicely over the entire image. because now it becomes a 6 by 6 with the padding, which is evenly fits our 2 by 2. And our output will end up being 3 by 3 in the end. So what we get is, by running our kernel over our image, we get an output which contains only the most prominent features of our original image. And this can be helpful for a variety of reasons, not just including the most prominent features, but also by reducing noise, allowing us to more easily perform operations such as translations. We can do more complex patterns on smaller images, especially with the limited memory capacity of TempleOS. And so there's lots of benefits to using max pooling, and this is not the only way to extract prominent features from an image. There are other ways, but this is one of the most straightforward ways. And there's actually general formulas that we can use to help us understand how to apply kernels and max pooling algorithms in code. So for example, to calculate the size of our output given any given size input and kernel size, the general formula for that is going to be n minus f over the stride plus 1, where n is the length in one direction and f is the length of our kernel in one direction. So in this case it's a 5 by 5, so the formula is the same, and it's a 2 by 2. It's the same for both the length and width. But if, for example, it was a 6 by 6, so in this case it would be 6 minus 2 over our stride of 2, which is 4 over 2, which is 2 plus 1 is 3. And it's the same, we can see it's the same because our dimensions are the same. But you would run this for either dimension. So if it was a 6 by 7, you would do 7 minus 2 over 2, which would leave you with 5 over 2, which in this case where we have a half, we actually are going to round. So we would round down to 2.5 plus 1 is 3. Again, in this case, we would have 3. Because we are applying our padding, we're never going to have these 0.5 values, so we don't have to worry about them so much. If we want to avoid these situations where we end up with 0.5s, we have to use a formula, and I'm going to rewrite it here because I wrote it wrong the first time. Take the max value between 0, so in this case our formula might give us negative numbers. We don't need a negative padding. We only ever want to use positive padding. So between 0 and, we have a couple of variables here, the width of the kernel minus the width of the input modulo by the stride width modulo again by the stride width. So we take the width of the kernel, subtract the size of the input. So back up to here we can see we would go from 5 to 3, and then we modulo by the size of the stride. So 5 minus 2 equals 3. Modulo the stride will give us 1. Modulo the stride again gives us 1. So this second modulo is really important because that's what's actually going to give us how much is left after the stride has run its course. So in this case, we only add 1 to the width to get 1 extra padding. And we can divide this number in larger cases. We just divide it by 2 to get how much to add to this side and how much to add to the left side. So we run this formula on both height and width. So it would be the same thing, except you would replace the width of the kernel and the width of the input and the width of the stride by the stride that and the input and the kernel in the height dimension. And we have to keep in mind that this is, in reality, it's a cube. We were running this just on the red channel, but each image composes a red, green, and blue. So by running max pooling operations on all 3 dimensions of our tensor, we can extract the most prominent and least noisy features of our image, and then we can redraw it on the screen. So let's do that now. So here we are in the temple, and I'm not going to do this thing where I retype the code. If you want to see my work process, I'll be streaming tomorrow, Sunday, at UTC +2, 7 p.m. For you guys in the US, that's 1 p.m. Eastern Standard Time. So I'll be streaming, and we'll do some Bible study. We'll do some, I'm going to try and refactor some of the tensor code. We'll be working on the source port of the Doom engine. So check out that stream tomorrow if you want to see the process for how I code these things. But for now, I'm just going to show off the code itself. So we can go into BMP view here and see that I've modified it slightly so that we can actually read from the tensors. So in the last video about tensors, we wrote to tensors, but now we're actually reading from tensors and viewing them on the screen. You can see we take a file name, we can convert that file to a tensor, then we read in that tensor in our initialization using this function BMP tensor read. And then we can display it to the screen just as easily because this function returns a CDC or device context. We could test out this function by uncommenting just the CD and main function call and pressing F5. And we'll be able to see very shortly here the picture of the cat being displayed normally. So let's jump into BMP file to tensor. You can see here an RGB tensor. This has been modified so that we have this BMP file to tensor function, which takes in the file name that we want to convert to a tensor and returns the new tensor. All of that is something that we've gone over already. With BMP tensor read, we can actually take that created tensor and, whether or not we want dither, return a new device context. In order to do that, we just need to retrieve the width and height by getting it from the tensor shape, and we can declare a new device context using that specified size. From there, we can retrieve the color values into this CBGR structure and save it and return it into this BMP24 color, which takes that structure and then converts it to a color which is in this file BMP class here, and it takes in that structure pointer as well as the dither probability. What the dither probability does is, rather than just checking if the RG or B value is high enough and then displaying that color, we use the element K to introduce a little bit of randomness into the equation so that each time we render on the screen, we are getting some kind of dithering or partial color effect. All of that is just reading from the tensors that we've established and redisplaying them on the screen. Now that we can do that, we can do some translations or manipulations such as the max pooling algorithm. And those functions are contained in this PER, which stands for perceptron policy file. In our main precept, I guess it doesn't matter, how you pronounce that. But in this main function here, you can see that there's some nested functions. The first one that we are using is that BMP file to tensor, which we've gone over. Then we apply the max pooling using a specified stride and size. Max pooling takes the tensor 3D of our BMP as well as the side and the stride, and it returns a new tensor 3D in which the max pooling operation has been applied. The first step to the max pooling operation is applying the padding, and that's done through the zero pad tensor function, which I'll go into more detail later. We retrieve the size of the image and the number of channels, as well as calculate using the n minus f over stride plus 1 function the output width and height. The channels are going to stay the same. The next few values here from area, AW, AH, max value, K, I, J, G, and stride increments I and J are all used as indexes to help us calculate the kernel output. I've drawn this little diagram to help explain the next part of this code. As you can see, two squares here on the screen, and these represent a kernel of size 2 by 2 and of size 3 by 3. In each position of the kernel, we can see the index. So at 0, 0 is the first index, 0, 1 is the added width index, 1, 0 is the added height, and 1, 1 is the last index value. What we want to do then is every time the width is minus 1 the size, so this is a 2 by 2, we want to subtract the width back to 0 and then add 1 to the height. And we know we're done with reading each row when we get to this value here. If we add 1 to this first value and add 1 to this second value, we'll have 2 and 2, and 2 times 2 will always equal the area. So by adding 1 to the index of the width and the index of the height, and then multiplying them together will tell us if we have reached the last tile. You can see the same thing happen here. So on 2, we're checking this if statement every time, but in this case, when we get to position 2, 2, if we add 1 to each, we'll get 3, 3. 3 times 3 equals the area of 9, and it would be the same thing on a 4 by 4 kernel or 5 by 5 kernel. We would always add 1 to the index and then multiply them together to see if we're at the last index. So you can see that's what happens here. We create our output and kernel matrix, and then we loop through the output, and while the width index times the height index plus 1 is not equal to the area, we need to retrieve the current value. So K is our temporary value, where we retrieve from the original tensor, and if K is larger than the max value, then we reset our max value. Once we've gone through this entire while loop, we know we're on the last tile, so we run that operation one last time. And at this point, in all the positions in the kernel, we have retrieved the max value and can set the output to our new max value. This stride increment here is used to shift the kernel along the original input image depending on the stride. So the stride gets added each time to both the J and I, in this case, width and height. Zero pad tensor is a function in our Tensor 3D class. God said about this function, "Forth sings immense unawares," so we're really entering some uncharted territory here. This function takes in our original image as well as the size and stride of the kernel, and it will return the tensor with the padding applied. We set up our variables here by just retrieving the input with height and dimension in the Z, so in this case it's the channels. And we also have some helper variables here which store the amount of padding as well as some temporary values for storing the values from the tensor. So A, B, C, and I and J are used for our for loop at the bottom here. We determine if calculating padding is even necessary. So for example, if in either dimension the stride is evenly divisible into the width or the height, then we know we don't even need to apply any padding. And if both the padding and the width and the height are equal to 0, then we don't need to change anything. We can just return the original image. We can see here in pad H is getting and pad W is getting set to the formula that we went over in the paper section of this video. Once we've created the new tensor with the correct size, then it's just a problem of adding the original values from the previous tensor, ignoring the areas which include padding. So from that we just take the width and height and subtract the amount of padding from each side. So if we are inside the bounds of that subtraction, then we just retrieve the values as they were originally in the tensor, but if we're outside, we're going to leave them as zeros. When we create a new tensor, it automatically gets initialized with zeros, so we could just think of this as like a portrait or the framing. It's kind of just taking the image and centering it in between our padding. By pressing F5 here, I can run the perceptron and it will go through each pixel and apply the max pooling algorithm. The padding is already complete. It's just running through each channel of the image and applying the max pooling operation. So this one is about 180 times it needs to apply this operation, and then it does it 3 times. It's 186, and it does it 3 times for each channel. So I'm just going to skip ahead here so that we can see the final result. So here we can see the image has been condensed. It's a lot smaller. There's been some padding applied so that the stride can easily go across it. And overall, it's just a lot of simpler and condensed image. We can try and run this program again using a different stride and size. So let's do something a little larger. So let's see what kind of output we get this time. So here we can see that as we increase the stride and the size, our image gets more and more base of its elements. You can see just barely the table here. You could see maybe the shadow of a cat, you know. The more you increase the stride, the more you're going to get these kind of lasering effects where you're going to get some red and green. But the more that you increase the size, it's going to make the image smaller and smaller because there's less pixels. So this one's obviously very small, but that's what allows us to, during the testing phase of our CNN, to really find what will be the best stride and size for our particular purpose, which is, in this case, image recognition. So that's going to be it for today. Remember to check out the stream tomorrow at 7 p.m. UTC+2 or 1 p.m. EST. That should be pretty fun, and like this video if you found it helpful. Subscribe and check out our website if you want to learn more about Terry Davis and the church. And you know, if there's something else you guys would rather see, let me know in the comments. You know, it really makes me feel good to read all your comments, and I love hearing from you guys. So take care until next time. Go with God. Godspeed. God bless. Adios.